What if everything you see around you, the stars, the planets, even the screen you're staring at right now, is just a tiny fraction of what's actually out there? What if I told you that 95% of the universe is completely invisible to us? That's right, the cosmos we think we know is just the tip of the iceberg. The rest, it's made up of two of the most mysterious and mind-bending forces in existence: dark matter and dark energy. These invisible giants don't just exist in the shadows, they shape the very fabric of the universe, holding galaxies together and pushing the cosmos apart at the same time. But here's the kicker: despite being the dominant forces in the universe, we still don't fully understand what they are. That's what makes them so fascinating. So, if you've ever wondered what's really out there beyond the stars, or why the universe behaves the way it does, you're in the right place. Over the next few minutes, we're diving into 25 mind-blowing facts about dark matter and dark energy that will completely change how you see the cosmos. Trust me, by the end of this, you'll be looking at the night sky in a whole new way, ready to unravel the mysteries of the invisible universe. Let's get started. Now, turning to our first fact, let's talk about just how much of the universe is made up of dark matter. Believe it or not, dark matter accounts for 27% of the entire universe. That's more than a quarter of everything that exists. To put that into perspective, all the stars, planets, galaxies, and even the dust and gas we can see make up less than 5% of the universe. That means dark matter outweighs visible matter by more than 5 times. This staggering realization completely reshaped our understanding of the cosmos. For centuries, scientists thought that what we could see was all there was. But the discovery of dark matter turned that idea on its head. It showed us that the universe is far more complex and mysterious than we ever imagined. Scientists are fascinated by dark matter because it doesn't just exist, it dominates. Its gravitational pull shapes the structure of galaxies and galaxy clusters, holding them together in ways that visible matter alone never could. Yet, despite its overwhelming presence, we still can't see it, touch it, or even fully understand it. That's what makes dark matter one of the greatest puzzles in modern science. Now, turning to our second fact, let's explore the even more mysterious force that dominates the cosmos: dark energy. While dark matter makes up 27% of the universe, dark energy accounts for a staggering 68%. That's more than 2/3 of everything that exists. Unlike dark matter, which holds galaxies together with its gravitational pull, dark energy does something entirely different. It pushes the universe apart. In the late 1990s, astronomers made a groundbreaking discovery. The universe isn't just expanding, it's expanding at an accelerating rate. This was a shock to the scientific community, as it defied the long-held belief that gravity would eventually slow down the expansion. But dark energy, this invisible and enigmatic force, is driving the universe to stretch faster and faster over time. Imagine blowing up a balloon, but instead of slowing down as it gets bigger, it starts inflating even more rapidly. That's what dark energy is doing to the cosmos. This discovery completely overturned our understanding of physics and the fate of the universe. Instead of a universe that might one day collapse back on itself in a big crunch, we now live in a reality where the universe could expand forever, growing colder and more distant as dark energy continues to dominate. Scientists are still grappling with what dark energy actually is. Some theories suggest it could be a property of space itself, often referred to as the cosmological constant, a concept even Einstein toyed with before dismissing it. Others propose it might represent a new, unknown force in the universe. Whatever it is, dark energy remains one of the greatest mysteries in science, challenging everything we thought we knew about the cosmos. Now, turning to our third fact, let's dive into the elusive nature of dark matter. Unlike the stars, planets, and gas clouds we can see, dark matter doesn't emit, absorb, or reflect light. That's why it's completely invisible to our telescopes, But if we can't see it, how do we even know it's there? The answer lies in its gravitational effects. Scientists first noticed something strange when they studied the way galaxies rotate. The outer regions of galaxies were moving much faster than expected, as if there was some invisible mass pulling on them. This invisible mass, dark matter, creates a gravitational force strong enough to hold galaxies together, even though we can't see it directly. Another clue comes from galaxy clusters, where the gravitational pull of dark matter bends light from distant objects, a phenomenon known as gravitational lensing. This bending of light allows astronomers to map the distribution of dark matter, even though it remains hidden from our eyes. So, while dark matter might be invisible, its effects are undeniable, shaping the very structure of the universe in ways we're only beginning to understand. Now turning to our fourth fact, let's explore the groundbreaking discovery of dark energy. In 1998, astronomers made a startling revelation that would change our understanding of the universe forever. Two independent teams of researchers were studying distant supernova exploding stars. To measure how fast the universe was expanding, they expected to find that the expansion was slowing down due to gravity's pull. But instead, they discovered the opposite. The universe was expanding at an accelerating rate. This unexpected finding pointed to the existence of a mysterious force counteracting gravity, which we now call dark energy. The discovery was so significant that it earned the researchers the Nobel Prize in Physics in 2011. This moment marked a turning point in cosmology, revealing that dark energy makes up about 68% of the universe and is driving its accelerated expansion. It's a reminder that even the most fundamental assumptions about the cosmos can be upended, opening the door to new questions and possibilities. As we continue to study dark energy, its true nature remains one of the greatest mysteries in science, challenging us to rethink the very fabric of reality. Now turning to our fifth fact, let's dive into the invisible force that keeps galaxies intact, dark matter. Imagine a galaxy spinning through space with stars, gas, and dust all moving at incredible speeds. Without something holding it all together, the sheer momentum of these objects would send them flying apart, scattering into the void. That's where dark matter comes in. Though we can't see it, dark matter's gravitational pull acts like a cosmic glue, binding galaxies together and maintaining their structure. Without it, galaxies as we know them simply wouldn't exist. Scientists first realized the importance of dark matter when they observed that galaxies were rotating much faster than expected based on the visible matter alone. The only explanation was that there had to be an unseen source of gravity, dark matter, providing the extra pull needed to keep everything in place. This discovery not only solved a major puzzle in astronomy, but also revealed that dark matter is essential for the large-scale structure of the universe. It forms a vast, invisible scaffold that shapes the distribution of galaxies and galaxy clusters, connecting them in a cosmic web. So, while dark matter remains hidden from our eyes, its influence is everywhere, holding the universe together in ways we're only beginning to understand. As we continue to explore this mysterious substance, one thing is clear: dark matter is the unsung hero of the cosmos, quietly ensuring that galaxies and the universe itself stay intact. Now turning to our sixth fact, let's explore the mysterious force that's doing the exact opposite of dark matter, dark energy. While dark matter holds galaxies together, dark energy is working to push the universe apart. Imagine the universe as a giant rubber band. If you stretch it, the rubber band expands, and the more you pull, the faster it stretches. That's essentially what dark energy is doing to the cosmos. It's a strange, invisible force that counteracts gravity, causing the universe to expand at an accelerating rate. This discovery, made in the late 1990s, completely changed our understanding of the universe's fate. Instead of slowing down due to gravity, as scientists once thought, the expansion of the universe is speeding up. Think of it like this: If you throw a ball into the air, you'd expect it to slow down and fall back to Earth because of gravity. But with dark energy, it's as if the ball keeps going faster and faster, defying gravity entirely. This acceleration is driven by dark energy, which makes up about 68% of the universe. Unlike matter or radiation, dark energy's density doesn't decrease as the universe grows. Instead, it remains constant, meaning its influence becomes stronger over time. This has profound implications for the future of the universe. If dark energy continues to dominate, the universe could keep expanding forever, growing colder and emptier as galaxies drift farther apart. So, while dark matter holds the cosmos together, dark energy is the force that's pulling it apart, shaping the ultimate destiny of everything we know. As we unravel this cosmic mystery, one thing is certain: dark energy is rewriting the rules of the universe, challenging our understanding of space, time, and the very fabric of reality. Now turning to our seventh fact, let's dive into one of the most intriguing possibilities about dark matter, what it's actually made of. Scientists have proposed a leading candidate called weakly interacting massive particles, or WIMP for short. These hypothetical particles are thought to be massive, as their name suggests, but they interact so weakly with ordinary matter and light that they're nearly impossible to detect directly. Imagine trying to catch a ghost that passes through walls without leaving a trace. That's the kind of challenge researchers face when hunting for WIMP. Despite their elusive nature, WIMP are a strong contender for dark matter because their properties align with what we observe in the universe. For instance, they could explain why dark matter doesn't clump together like normal matter, but instead forms vast, invisible halos around galaxies. To find these mysterious particles, scientists have designed incredibly sensitive experiments deep underground, where they're shielded from cosmic rays and other interference. These detectors are designed to catch the rare moment when a WIMP might collide with an atomic nucleus, producing a tiny signal that could reveal its presence. So far, no definitive detection has been made, but the search continues with experiments like the Large Underground Xenon experiment and others pushing the boundaries of technology and patience. The discovery of WIMP would be a monumental breakthrough, not only solving the mystery of dark matter, but also opening a new window into the fundamental nature of the universe. As we wait for answers, one thing is clear: the hunt for WIMP is a testament to human curiosity and our relentless drive to uncover the secrets of the cosmos. Now turning to our eighth fact, let's explore the fascinating idea that dark energy might not be some exotic substance, but rather an inherent property of space itself. This concept is often referred to as the cosmological constant, a term first introduced by Albert Einstein over a century ago. Back then, Einstein was trying to reconcile his equations of general relativity with the idea of a static universe, one that wasn't expanding or contracting. To make his equations work, he added this constant, which he later called his biggest blunder when the universe was found to be expanding. But here's the twist: decades later, the discovery of dark energy brought the cosmological constant back into the spotlight. Scientists now believe that this constant might represent the energy of empty space itself, a kind of background energy that permeates the entire universe. Unlike matter or radiation, which dilute as the universe expands, this energy density remains constant, meaning it doesn't weaken over time. This is why dark energy becomes more dominant as the universe grows, driving its accelerated expansion. It's as if space itself has a built-in stretching mechanism, pushing galaxies apart faster and faster. This idea ties directly into Einstein's original equations, showing how his blunder might actually be one of the most profound insights into the nature of the cosmos. The cosmological constant also raises deep questions about the fabric of reality. What is space, really, if it can possess energy and influence the fate of the universe? As we continue to study dark energy, This connection to Einstein's work reminds us that even the greatest minds can leave behind mysteries that take generations to unravel. And with that, we move closer to understanding the true nature of the universe's most enigmatic force. Now turning to our ninth fact, let's delve into how dark matter leaves its mark on the cosmic microwave background, often referred to as the afterglow of the Big Bang. This faint radiation, which fills the entire universe, is like a snapshot of the cosmos when it was just 380,000 years old. At that time, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. But here's where dark matter comes into play. Even though it doesn't interact with light, its gravitational pull influenced the distribution of matter in the early universe. These subtle gravitational effects caused tiny fluctuations in the density of matter, which in turn left imprints on the cosmic microwave background. When scientists study these patterns, they can see how dark matter shaped the universe's structure from its earliest moments. These imprints are like cosmic fingerprints, providing crucial evidence for dark matter's existence and helping us map its distribution across the universe. Without dark matter's gravitational influence, the universe as we know it, with its galaxies, clusters, and vast cosmic web, would look very different. So, the next time you hear about the cosmic microwave background, remember that it's not just a relic of the Big Bang. It's also a treasure trove of clues about the invisible force that holds our universe together. And with that, we move closer to unraveling the mysteries of dark matter and its role in shaping the cosmos. Now turning to our 10th fact, let's explore the intriguing possibility that dark energy might not be as constant as we once thought. For years, scientists have assumed that dark energy's strength remains steady over time, acting as a consistent force driving the universe's expansion. But what if that's not the case? Recent theories suggest that dark energy's influence could change over time, potentially altering the fate of the universe in dramatic ways. Imagine dark energy growing stronger, accelerating the expansion of the universe even faster than it does today. This scenario could lead to what's known as the Big Rip, where galaxies, stars, and even atoms are torn apart as the universe expands uncontrollably. On the other hand, dark energy could weaken, allowing gravity to regain dominance and possibly leading to a big crunch where the universe collapses back in on itself. Or it might fluctuate unpredictably, creating a cosmic tug of war between expansion and contraction. These possibilities challenge our understanding of the universe's future and raise profound questions about its ultimate destiny. Could the fate of everything we know hinge on the behavior of this mysterious force? As scientists continue to study dark energy, they're searching for clues in the distant universe, observing how its effects have evolved over billions of years. The answers they uncover could reshape our understanding of time, space, and the very fabric of reality. So, while dark energy remains one of the greatest mysteries in science, its potential to change over time reminds us that the universe is far more dynamic and unpredictable than we ever imagined. And with that, we move closer to uncovering the secrets of dark energy and its role in shaping the cosmos. Now turning to our 11th fact, let's dive into the fascinating role dark matter plays in shaping the universe on a grand scale. Dark matter doesn't just float around aimlessly, it forms vast, intricate structures known as cosmic webs. Picture this, an enormous, invisible network stretching across the universe, acting as the scaffolding for galaxies and galaxy clusters. These cosmic webs are like the hidden framework of the cosmos, guiding where galaxies form and how they cluster together. Without dark matter's gravitational pull, galaxies would be scattered randomly, and the universe as we know it wouldn't exist in its current form. Scientists have mapped these cosmic webs by observing how galaxies are distributed and how their light bends due to dark matter's gravitational influence. It's like tracing the outline of something invisible by studying its effects on the visible world. These webs aren't just static structures, they're dynamic, evolving over billions of years as dark matter interacts with itself and with the galaxies it holds together. The discovery of cosmic webs has given us a deeper understanding of how the universe is organized on the largest scales, revealing a hidden architecture that connects everything in the cosmos. So, while we can't see dark matter directly, its presence is undeniable, weaving the very fabric of the universe into the intricate patterns we observe today. And with that, we move closer to unraveling the mysteries of dark matter and its role in the cosmic dance of galaxies. Now turning to our 12th fact, let's explore how dark energy has completely reshaped our understanding of the universe's ultimate fate. Before dark energy was discovered, many scientists believed in the Big Crunch theory, a scenario where the universe's expansion would eventually slow down, stop, and reverse, causing everything to collapse back into a single point. It was a dramatic vision of the cosmos, like a cosmic rubber band snapping back after being stretched. But dark energy changed everything. When astronomers observed distant supernova in the late 1990s, they found that the universe wasn't just expanding, it was accelerating. This shocking discovery pointed to the existence of dark energy, a mysterious force pushing galaxies apart faster and faster. Instead of a big crunch, dark energy suggests a very different future, an ever-expanding universe where galaxies drift farther and farther apart, eventually becoming so distant that their light can no longer reach us. This idea challenges not only the Big Crunch but also our fundamental understanding of gravity and the forces that govern the cosmos. Dark energy's dominance means the universe might continue to expand forever, growing colder and emptier over time. It's a profound shift in our cosmic perspective, showing that the universe's fate is far more complex and mysterious than we once imagined. And as we continue to study dark energy, we're left with even bigger questions. What exactly is this force? Will it change over time? And what does it mean for the ultimate destiny of everything we see in the night sky? These are the puzzles that keep scientists searching for answers, as dark energy continues to challenge our understanding of the universe's grand story. Now turning to our 13th fact, let's dive into a fascinating hypothesis about dark matter. Could it be made up of primordial black holes? These aren't the black holes we typically think of, formed from collapsing stars. Instead, primordial black holes are thought to have been created in the chaotic moments just after the Big Bang, when the universe was incredibly dense and hot. Imagine tiny ripples in the fabric of space-time collapsing under their own gravity, forming black holes no larger than an atom or as massive as a star. Scientists have long wondered if these ancient objects could account for the mysterious dark matter that holds galaxies together. If true, it would mean that dark matter isn't made of exotic particles like WIMP or Axions, but rather of these ancient cosmic relics. To test this idea, researchers are looking for clues in the way light bends around massive objects, a phenomenon called gravitational lensing. If primordial black holes exist, they should occasionally pass in front of distant stars, causing a brief but detectable flicker in their light. So far, no definitive evidence has been found, but the search continues. This hypothesis opens up a whole new way of thinking about dark matter, suggesting that the answer to one of the universe's biggest mysteries might lie in its earliest moments. As we explore this possibility, we're reminded once again of how much we still have to learn about the cosmos and the forces that shape it. Now turning to our 14th fact, let's explore a mind-bending idea. Could dark energy be a fifth fundamental force in the universe? We're all familiar with the four known forces: gravity, electromagnetism, and the strong and weak nuclear forces that govern everything from the motion of planets to the behavior of atoms. But dark energy, with its mysterious ability to accelerate the expansion of the universe, might represent something entirely new. Imagine a force that doesn't just pull or push like gravity or electromagnetism, but one that stretches the very fabric of space itself. This hypothetical fifth force could be the key to understanding why the universe is expanding faster and faster, defying the pull of gravity that should be slowing it down. Scientists are still grappling with how this force might work, but if it exists, it would fundamentally change our understanding of physics. It would mean that the universe is governed by more forces than we've ever imagined, and that dark energy isn't just a mysterious energy field but a whole new kind of interaction. As researchers continue to study the cosmos, they're searching for clues that could reveal whether this fifth force is real, and if it is, what it means for the fate of the universe. This possibility reminds us that even the most fundamental laws of nature might still hold secrets waiting to be uncovered. Now turning to our 15th fact, let's dive into how dark matter interacts with light in a way that's both fascinating and incredibly useful for scientists. Dark matter, despite being invisible, has a profound effect on the light traveling through the universe. This phenomenon is known as gravitational lensing. Imagine light from a distant galaxy traveling across the cosmos, only to encounter a massive cluster of dark matter along its path. The immense gravitational pull of this dark matter bends the light, much like a magnifying glass bends and focuses sunlight. This bending creates distorted or magnified images of the distant galaxy, sometimes even forming multiple images or rings of light. Astronomers use this effect to map the distribution of dark matter in the universe, essentially turning these distortions into a cosmic blueprint. By studying how light bends around galaxies and galaxy clusters, scientists can infer where dark matter is concentrated and how it shapes the large-scale structure of the cosmos. Gravitational lensing not only reveals the presence of dark matter, but also provides a powerful tool for exploring the universe's most hidden corners. It's a reminder that even though we can't see dark matter directly, its influence is written across the sky in the light of distant stars and galaxies. Now turning to our 16th fact, let's explore a theory that sounds like something straight out of a science fiction movie, but is grounded in real scientific speculation. This is the Big Rip theory, and it's a scenario where dark energy's mysterious and growing influence could lead to the ultimate cosmic catastrophe. Here's how it works. Dark energy, as we've discussed, is driving the universe's expansion at an accelerating rate. But what if this acceleration doesn't just continue? What if it gets stronger over time? The Big Rip theory suggests that dark energy's strength could increase to the point where it overcomes all other forces in the universe. First, it would tear apart galaxies, pulling them away from each other faster than the speed of light. Then, it would rip apart stars and planets, dismantling solar systems. Eventually, even atoms themselves wouldn't be safe. The fabric of space-time would stretch so violently that the bonds holding particles together would break, leaving the universe as a cold, empty void. While this might sound terrifying, it's important to note that this scenario is still just one of several possible futures for our universe. Scientists are actively studying dark energy to understand whether its strength will remain constant, increase, or even decrease over time. The Big Rip is a stark reminder of how much we still have to learn about the forces shaping our cosmos, and how even the most fundamental aspects of reality could one day be rewritten by the unseen power of dark energy. Now turning to our 17th fact, let's dive into a fascinating discovery that could change how we think about dark matter. For decades, scientists believed that dark matter only interacts with the universe through gravity. But recent observations suggest there might be more to the story. Researchers have noticed strange behavior in galaxy clusters, where dark matter appears to interact with itself in ways that go beyond just gravitational pull. For example, in the Bullet cluster, a collision between two galaxy clusters revealed that dark matter from each cluster passed through each other without slowing down, while the normal matter collided and heated up. This observation hints that dark matter particles might have some form of interaction with each other, possibly through a new, unknown force. This idea opens up exciting new avenues for research as scientists explore whether dark matter particles could collide, scatter, or even exchange energy in ways we haven't yet detected. If confirmed, this would mean dark matter isn't just a passive player in the cosmos. It could have its own complex physics, adding another layer of mystery to this already enigmatic substance. As we continue to study these interactions, we might uncover clues that help us finally understand what dark matter truly is and how it shapes the universe we live in. Now turning to our 18th fact, let's explore a surprising twist in the story of dark energy, one that takes us back to the early 20th century and the work of Albert Einstein. When Einstein developed his theory of general relativity, he introduced a term called the cosmological constant. At the time, he believed the universe was static and unchanging, and this constant was meant to balance the equations to prevent the universe from collapsing under gravity. However, when Edwin Hubble discovered that the universe was actually expanding, Einstein famously called the cosmological constant his greatest blunder and abandoned the idea. But here's where it gets fascinating. Decades later, the discovery of dark energy brought the cosmological constant back into the spotlight. Scientists realized that this term, once thought to be a mistake, could actually explain the mysterious force driving the universe's accelerating expansion. Today, the cosmological constant is a cornerstone of our understanding of dark energy, showing how even a discarded idea can resurface to solve one of the biggest mysteries in science. It's a reminder that in the quest to understand the cosmos, sometimes the answers are hidden in plain sight, waiting for the right moment to be rediscovered. Now turning to our 19th fact, let's dive into another intriguing possibility in the search for dark matter, axions. These hypothetical particles are among the leading candidates for what dark matter might be made of. Unlike the more commonly discussed weakly interacting massive particles, or WIMP, axions are incredibly light and interact even more weakly with ordinary matter. They were first proposed in the late 1970s to solve a problem in particle physics related to the strong nuclear force, but scientists soon realized they could also explain dark matter. Axions are so elusive that they barely interact with anything, making them nearly impossible to detect directly. However, researchers are not giving up. Experiments like the Axion Dark Matter Experiment, or ADMX, are using powerful magnetic fields and ultra-sensitive detectors to try and catch these ghostly particles. The idea is that axions in the presence of a strong magnetic field might convert into detectable photons, giving scientists a rare glimpse into their existence. While no axions have been found yet, the search continues, driven by the tantalizing possibility that these tiny particles could hold the key to unlocking one of the universe's greatest mysteries. It's a reminder that sometimes the answers we seek might come from the most unexpected places. Now turning to our 20th fact, let's explore one of the most puzzling aspects of dark energy. Its density remains constant even as the universe expands. This is a stark contrast to matter and radiation, whose densities decrease as the universe grows larger. Think of it like this. If you had a balloon filled with air, the air molecules inside would spread out as the balloon expands, becoming less dense over time. But dark energy doesn't behave this way. Instead, its density stays the same, no matter how much the universe stretches. This counterintuitive property is what allows dark energy to dominate the cosmos over time, driving the accelerated expansion of the universe. While matter and radiation become diluted as space expands, dark energy's unchanging density means its influence only grows stronger. This strange behavior challenges our understanding of physics and raises profound questions about the nature of space itself. Why does dark energy's density remain constant? What does this tell us about the fabric of the universe? These are the mysteries that keep scientists searching for answers as they try to unravel the true nature of this enigmatic force shaping the fate of our cosmos. Now turning to our 21st fact, let's dive into how dark matter shapes the rotation curves of galaxies. a discovery that fundamentally challenged our understanding of physics. In the early 20th century, astronomers expected that stars on the outer edges of galaxies would move slower than those near the center, much like planets farther from the Sun orbit more slowly. This was based on Newton's laws of gravity, which seemed to perfectly explain the motion of celestial bodies. But when scientists began measuring the rotation speeds of galaxies, they found something astonishing. Stars on the outer edges were moving just as fast as those near the center. This unexpected behavior couldn't be explained by the visible matter alone. The only way to account for these high speeds was to propose the existence of an invisible, massive substance exerting a gravitational pull, dark matter. This discovery was the first strong evidence for dark matter's existence, and it completely upended our understanding of how galaxies work. Without dark matter, galaxies would fly apart, unable to hold themselves together under the observed rotation speeds. This groundbreaking revelation not only reshaped astronomy, but also opened the door to a deeper exploration of the universe's hidden components. It's a reminder that even the most well-established laws of physics can be challenged by the mysteries of the cosmos. Now turning to our 22nd fact, let's explore the intriguing possibility that dark energy could be a quantum field. This idea connects dark energy to the strange and fascinating world of quantum physics, where even empty space is far from empty. In the quantum realm, particles constantly pop in and out of existence, creating what scientists call quantum fluctuations. These tiny, fleeting changes in energy are a fundamental part of how the universe operates at its smallest scales. Some researchers believe that dark energy might arise from these quantum fluctuations, suggesting that the very fabric of space itself holds a kind of energy that drives the universe's expansion. This concept ties back to Einstein's cosmological constant, which he initially introduced as a mathematical fix to his equations but later abandoned. However, with the discovery of dark energy, the cosmological constant has made a comeback, and the idea that it could be linked to quantum fields has gained traction. If dark energy is indeed a quantum field, it would mean that the vast, empty stretches of space are teeming with energy, constantly pushing the universe to expand faster and faster. This connection between the largest and smallest scales of the cosmos is one of the most mind-bending aspects of modern physics, reminding us just how much we still have to learn about the universe. As we continue to unravel these mysteries, the interplay between dark energy and quantum physics could hold the key to understanding the ultimate fate of everything we see and everything we don't. Now turning to our 23rd fact, let's dive into one of the most radical ideas in modern cosmology, the possibility that dark matter might have existed even before the Big Bang. This theory challenges our conventional understanding of the universe's origins, suggesting that dark matter could be older than the cosmos itself. According to some speculative models, dark matter might have formed in a previous phase of existence, perhaps during a pre-Big Bang era. These theories propose that the universe we know today could be just one chapter in a much larger cosmic story, with dark matter serving as a relic from an earlier epoch. If true, this would mean that dark matter isn't just a mysterious component of our universe, it could be a bridge to an entirely different reality, one that predates time and space as we understand them. While this idea remains highly speculative, it opens up fascinating questions about the nature of existence and the possibility of multiple cosmic cycles. Could dark matter be the key to unlocking secrets about what came before the Big Bang? As scientists continue to explore these mind-bending theories, the idea that dark matter might predate the universe itself reminds us just how much we still have to discover about the cosmos and its deepest mysteries. Now turning to our 24th fact, let's explore an idea that stretches the boundaries of our imagination, the possibility that dark energy could be the driving force behind the existence of a multiverse. If dark energy is responsible for the accelerating expansion of our universe, as current evidence suggests, it might also play a role in creating entirely separate universes beyond our own. This concept, known as the multiverse theory, proposes that our universe is just one of countless others, each with its own unique physical laws and properties. Dark energy's mysterious influence could be the key to understanding how these universes form and evolve. Some theories suggest that dark energy might cause regions of space to expand so rapidly that they pinch off into their own independent universes, forever disconnected from ours. This idea not only challenges our understanding of reality, but also raises profound questions about the nature of existence. Could there be other versions of us living in parallel universes shaped by different rules? While the multiverse remains a speculative concept, it's a fascinating reminder of how much we still have to learn about dark energy and its potential to reshape our understanding of the cosmos. As scientists continue to investigate this mind-bending possibility, the idea of a multiverse fueled by dark energy invites us to imagine a reality far grander and more complex than we ever thought possible. Now turning to our 25th and final fact, we arrive at the heart of the cosmic mystery. Dark matter and dark energy remain two of the greatest unsolved puzzles in modern science. Despite decades of research, we still don't know what dark matter is made of or how dark energy works. These invisible forces dominate the universe, making up 95% of its total content, yet they elude our detection and understanding. Scientists have proposed countless theories and conducted groundbreaking experiments, from particle colliders to space telescopes, but the true nature of these phenomena continues to evade us. What makes dark matter and dark energy so captivating is not just their mystery, but their profound implications for our understanding of reality. They challenge the very foundations of physics, forcing us to rethink the laws that govern the cosmos. Why does dark matter hold galaxies together without interacting with light? How does dark energy drive the universe's expansion at an ever-increasing rate? These questions remind us that the universe is far stranger and more complex than we ever imagined. And while the answers remain elusive, the pursuit of these mysteries inspires awe and curiosity, driving humanity's quest to uncover the secrets of the cosmos. As we stand on the edge of discovery, one thing is certain: dark matter and dark energy will continue to captivate scientists and dreamers alike, reminding us that the universe is full of wonders waiting to be revealed. Now turning to the future of dark matter and dark energy research, scientists are pushing the boundaries of technology and imagination to uncover the secrets of these cosmic enigmas. One of the most ambitious projects is the Large Hadron Collider, the world's most powerful particle accelerator. By smashing particles together at nearly the speed of light, researchers hope to detect elusive particles that could make up dark matter, such as weakly interacting massive particles, or WIMP. While no definitive discovery has been made yet, each experiment brings us closer to understanding the invisible forces shaping our universe. Meanwhile, space telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are peering deeper into the cosmos than ever before. These instruments are designed to map the distribution of dark matter through gravitational lensing and study the effects of dark energy on the universe's expansion. By observing distant supernova, galaxy clusters, and the cosmic microwave background, astronomers are gathering clues that could finally reveal the true nature of these mysterious phenomena. But the quest doesn't stop there. Future missions such as the European Space Agency's Euclid Telescope and the Vera C. Rubin Observatory's Legacy Survey of Space and Time aim to create the most detailed maps of the universe ever made. These projects will track billions of galaxies, measuring how dark energy influences their distribution and movement over time. Combined with advancements in quantum physics and theoretical models, these experiments could revolutionize our understanding of the cosmos. As we look ahead, the pursuit of dark matter and dark energy represents one of the most exciting frontiers in science. It's a journey that challenges our deepest assumptions about the universe and pushes the limits of human ingenuity. And while the answers remain just out of reach, the discoveries waiting to be made promise to reshape our understanding of reality itself. Now turning to the philosophical implications of dark matter and dark energy, these cosmic mysteries don't just challenge our scientific understanding, they also force us to confront profound questions about the nature of reality itself. What does it mean that most of the universe is invisible to us? If dark matter and dark energy make up 95% of everything that exists, then what we see, stars, planets, and galaxies, is just a tiny fraction of the cosmos. This realization humbles us, reminding us how much we still don't know about the universe we call home. These mysteries also raise questions about our place in the grand scheme of things. If dark energy is causing the universe to expand faster and faster, what does that mean for the future of life? Could it one day tear apart the very fabric of space, or will it lead to a cold, empty cosmos where galaxies drift endlessly apart? These possibilities force us to reflect on the fleeting nature of existence and the impermanence of everything we hold dear. But perhaps the most intriguing philosophical question is this: are there limits to human knowledge? Dark matter and dark energy remind us that the universe is far stranger and more complex than we ever imagined. They challenge our assumptions about how the cosmos works and push us to rethink the very foundations of physics. Could there be aspects of reality that are forever beyond our understanding? Or will future breakthroughs reveal truth so profound that they reshape not just science but our entire worldview? As we grapple with these questions, one thing is clear: the pursuit of dark matter and dark energy isn't just about solving scientific puzzles. It's about exploring the deepest mysteries of existence and discovering what it means to be human in a vast, enigmatic universe. And while the answers may remain elusive, the journey itself is a testament to our curiosity, creativity, and unyielding desire to understand the cosmos. Now turning to the conclusion of our journey through the mysteries of dark matter and dark energy, let's take a moment to reflect on the 25 mind-blowing facts we've explored. From the staggering realization that dark matter makes up 27% of the universe to the mind-bending idea that dark energy accounts for 68%, these invisible forces have reshaped our understanding of the cosmos. We've seen how dark matter holds galaxies together, while dark energy drives them apart, creating a cosmic tug of war that defines the very structure of the universe. We've delved into theories about WIMP, Axions, and primordial black holes, and pondered whether dark energy could be a fifth fundamental force or even a quantum field. Each fact has revealed just how much we still don't know, and yet how much closer we're getting to unraveling these profound mysteries. These discoveries aren't just scientific milestones, they're windows into the very nature of reality. They challenge us to rethink what we know about space, time, and existence itself. They remind us that the universe is far stranger and more complex than we ever imagined, and that our journey to understand it is far from over. As we continue to explore, we're not just uncovering the secrets of dark matter and dark energy, we're also discovering what it means to be curious, resilient, and endlessly fascinated by the cosmos. So, what do you think about these cosmic mysteries? Do you have a favorite fact or theory that stood out to you? Share your thoughts in the comments below. I'd love to hear your perspective. And if you're as captivated by these topics as I am, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update. Together, let's keep exploring the wonders of the universe and uncovering the secrets that lie hidden in the dark. Thanks for watching, and until next time, keep looking up.